So you've already seen a couple of electrophilic addition mechanisms, and today we're going to look at another electrophile that will react with alkenes to give, well, something else. Here's an overall equation. We're going to use butene again. It's nice and convenient for our first few examples. There's a bit more to be said about other alkenes. And it'll actually react with sulphuric acid. Right? When it does, now there are a couple of steps here, but we get what we call, well, let me draw it first. We get what we call an alkyl hydrogen sulphate. So this one here is bute 2, and then that's where the connection is. So we'd call this one bute 2 alkyl hydrogen sulphate. I'm going to use an F instead of a PH today. Why not? Because there's not enough space. Right, hydrogen sulphate. There'd be another product there or not? Actually, the answer is no, because remember, this is an addition reaction. The idea that two reactants just add together. So H2SO4, the H, if I actually expand just one of the two H's that's on that carbon there, one of the H's from H2SO4 ends up on one carbon of the double bond, and the remainder, which is basically the OSO3H, we need to explain why it's through the O, ends up on the other carbon of the double bond. But as before, the reactant's been split basically and attached across the double bond. Now, a couple more things it's worth pointing out to you. Sulphuric acid's got an interesting chemical structure. We draw it as such, HOSOH. That can't be all of it because that's just H2SO2 at the minute. That sulfur we also consider to have two double bond O's on it. Okay, now yes, that does mean that there are 6 shared pairs of electrons around that sulfur, which means there's 12 electrons in total around that sulfur. That's totally fine. All right, so it's not actually capped at 8. Full outer shell of 8 electrons is like a really solid truth for like the period 2 elements. But period 3 elements, we're going to talk about this more in future topics, but basically sulfur, there's some d electrons. Now 3d, sulfur doesn't have any 3d electrons, but the 3d electron orbitals are quite close in energy to the 3p that we've got here in sulfur's outer shell. And basically 3d comes in and helps out a bit with the bonding. So it just is that way. 6 covalent bonds, 2 doubles and 2 singles. Sorry, 6 pairs of electrons, 4 covalent bonds, 2 doubles, 2 singles. Now, let's have a look at that structure. Let's apply what we are familiar with from bonding in general. We'd expect these hydrogens to be delta plus, just simply because they're bonded to oxygen, and oxygen is much more electronegative. So whenever you see an OH in any group, and here it's definitely not an alcohol because that's not a carbon, it's a sulfur, but because we've got that OH group there, 2 of them, we'd expect those bonds to be polarized. Now, sulfuric acid is a strong acid, which means if you've got a bottle of sulfuric acid in the lab for doing a titration or whatever with, then the chances are that it's dissociated. It's fully dissociated, and you've got like a sulfate ion or something similar, and at least 1 H plus per acid coming off. Thing is, when it's concentrated, so if I'm using concentrated sulfuric acid, then there isn't much water for those H pluses, those acidic hydrogens, to drop off into. And so I think it's probably best at this point, because we've still got the acids and bases topic to come at the end of year 12 as well, if I just say that in concentrated sulfuric acid, the main species present is that, and we'd call that undissociated, i.e. having not broken apart sulfuric acid. Now, I also want to point out this organic product here, we're calling it bute 2-alkyl hydrogen sulphate. Can I just remind you that hydrogen sulphate is this ion, HSO4 minus. And HSO4 minus would simply be, well, very, very similar to H2SO4 minus a H plus, hence it being HSO4 minus, but it would be that with a negative charge on the O. Now, we haven't drawn any lone pairs yet, and we'll save the lone pairs when we look at the mechanism, but this here is a hydrogen sulphate ion, and you can see that perhaps through the oxygen atom there, I will draw the lone pairs actually, 3 lone pairs on there, it could form a bond with a carbon somehow. So maybe you can see now, knowing what you've seen already for about electrophilic addition, how this might come together. Anyway, let's look at the mechanism, let's deal with it, and there's a bit more we can say afterwards on this one as well. So we're going to stick with butene for a little bit longer as our alkene of choice. The reason for that is because it's symmetrical. So there's only one possible product. Next lesson we'll start talking about alternative products and major minor products. There's more to say about that. So butene plus concentrated sulphuric acid. Now, as before, we don't really want to be drawing our mechanisms in skeletal style, even though we can handle it. And so I'm going to expand out the relevant parts of this structure. Don't really need to worry about the methyl groups on butene, apart from the fact they have to be there for the structure to be complete. But I don't need to expand them out with all the display. But the CC double bond obviously does definitely need to be shown. And I might as well show those H's there just to make sure the structure is nice and neat. Now, we're going to draw sulphuric acid in its full glory first of all, but then you'll see that it's actually quite a lot more efficient for us just to write H and OSO3 H. Yeah. So for the second mechanism, when we do it again at the end, we'll see that H2SO4. Now there's our electrophile. Either of those hydrogens on the sulphuric acid molecule are sufficiently delta plus to get this reaction going. And so my first step, as we saw previously with other substances, is an arrow from the double bond to the delta plus hydrogen, okay, towards something partially positively charged, and here it's a delta plus hydrogen. As you know, hydrogen can only ever have one bond, and so if this bond here is being formed between one of those two carbons in the double bond and the hydrogen, then the hydrogen-oxygen bond must break. And so I'll show an arrow going from that hydrogen-oxygen bond, which means it's breaking to the O. Why would it go to the O? Well, it can't go to the H because the H has got 2 electrons coming in on the other side. And also the O is more electronegative than the H, so that's a sensible sort of logic behind the electrons go to the O, not anywhere else. Let's draw the intermediate now. Remember, we haven't got our final product yet. We're halfway there, or partway there. So that CC double bond is broken, and now it's a single bond. The 4 groups, that's a H and a methyl twice, which were attached to those double bond carbon atoms, are still all intact and bonded where they were before. And again, it's convenient using butene because it doesn't matter which carbon from the double bond to put this H on, it makes no difference to the outcome. So I'll just pop it on the one on the left, why not? So that carbon has now got a full outer shell, which for it is 8, and so that's all good. Remember that this carbon has only got 3 bonds. It's effectively just lost an electron because when this shared pair of electrons, half of the double bond, formed a bond with the H, this carbon kept its electron because it's still now being shared, but with something else, with a H instead of a C. But the other carbon, the one that didn't get the H, you could imagine it, the electron it put into that double bond has been lost. Either way, whenever carbon's got 3 bonds, it's C plus anytime that we see it. So we've got a carbocation again. We don't need to try and name that, but there it is. Next up then, now this is where it's basically the same as what we saw for hydrogen bromide before, except instead of Br minus, we've now got all of this minus. So what is all of this? Well, it's OSO3H. I'm still going to continue, just for this example, to draw it fully expanded. So let's just draw it like that. And again, let's think about the electrons now. This is where we do need to think lone pairs and make sure we keep track of everything. This oxygen in sulphuric acid, it's just like an oxygen in H2O really, i.e. it's an oxygen with 2 covalent bonds. And so it will also have 2 lone pairs. So we don't bother drawing them, but this O had 2 lone pairs on it. It's still got those 2 lone pairs, but now it's got another lone pair because when that HO bond broke, both electrons went into the outer shell of the O. So since I'm just using color coding here because I can, you don't have to, but that pair of electrons there, that pink line, is now a lone pair. Now, really all you have to show is one of those electron pairs. I've drawn all 3, but there's something else to note here, negative charge. Now, this O got an electron back from the OH bond that broke, but it also got the electron that you might imagine the hydrogen had put in. So it's now got like a bonus electron, and so it's O minus, right? That is our hydrogen sulphate ion, H2SO4 minus, just written, or rather drawn out in a display style. Now, all that detail aside, what do we need to do with this bit next? Well, we saw this before when we had HBr reacting with an alkene. we had a delta plus atom which formed a bond and got picked off and built into the double bond group as a CH bond. And then the carbocation, we say, got attacked or had a bond formed from one of the lone pairs on the negative ion. And so here I need to show a nice clear arrow coming from a lone pair on an O. Now that there doesn't look like a lone pair anymore. I've scribbled on it too much, so I better not use that one. So lone pair on an O, nice clear one, O minus at that, to the C plus. Think about it, this negative particle and that positively charged particle are going to be attracted, and the negatively charged atom, if this was a model, I could pick it up and it's going to like twist around and point towards, so that negative O atom is going to be attracted, and the outer shells are going to overlap between the C plus and the O minus, and electrons are going to be shared. So there is our product. Let's just draw it all out. We've got the 2 carbons from the double bond. Again, if I use these coloured pens just to really overdo the keeping track of what's what, I'll just put them in an orange box so you can see which ones they are on this next bit. You've got the C double bond, which is now a single bond. That's our 2 carbons there. I'm just putting them in a box so you can see, and that's not part of drawing the mechanism, drawing the box. There are now 2 H's on there where there was only 1 before, because of the H2SO4 has given one off as well. Methyl group. The other carbon, similar. It had a CH3 and a H. It's still got those, but now it's also got, well, the rest of the sulphuric acid molecule, which we can just write as OSO3H, like that. So you can see that's hydrogen sulphate connected. So how would we name this one? You saw earlier we wrote but2-yl hydrogen sulphate for a different structure. So how about you pause the video, have a quick think, have a guess basically, an educated guess. What might we call this? Sorry, I've just realised it's actually the same structure, isn't it? Don't bother pausing unless you've been falling asleep. 1, 2, 3, 4. It's the same molecule as before. I thought we'd drawn a different one. So this is still butyl, but more specifically but2-yl, because it could have been but1-yl. It would never have been 3 or 4 because they are 1 and 2, just with the wrong numbering. So this is but2-yl hydrogen sulphate. Now you might say, brilliant, but what's the point of that? What's that chemical used for? And I'd say, well, actually it's quite important because it's used in the production of alcohols. So there's another mechanism we'll study later on in the course where we look at an alkene turning directly into an alcohol by hydration, but this is another way of achieving the same thing. So I just want to summarise and then we'll go on to this making alcohols. There's the mechanism. If this was examinable, if this was an exam question, there'd be a mark for each of those arrows. Double bond to hydrogen delta plus, HO bond breaks, arrow to the O. Then there'd be a mark for this intermediate, this carbocation structure, which is correct there. Then there'd be a mark for that arrow, but that arrow encompasses all of this. Now, therefore, what I'm saying is it's H2SO4 minus is the formula of the thing that the arrow is coming from. More specifically still, has to be coming from a lone pair on an O, which isn't a part of an OH, so basically the single bond O minus. And that takes me to a final point, all for this 1 mark. The arrow has to be coming from the lone pair on that O of a negatively charged particle. So if you forget to put the negative charge on, if you forget to draw the lone pair, or if you show the arrow coming from a different O, then it's wrong and you don't get that mark. Okay, so 4 marks there. Could even be 5 marks if the question said name and outline the mechanism. Outline the mechanism is draw the mechanism. Name it is to call it what we know it to be, which is electrophilic addition. So name and outline the mechanism, name it and draw it. Now, let's go on then and talk about the fate of this alkyl hydrogen sulphate. It's quite reactive and it will quite easily react with H2O. So if I just make a bullet point note here, now you need to add this into your notes. The alkyl hydrogen sulphate will react with water, is what I'm about to put. The alkyl hydrogen sulphate, I'll say, will readily react with water. To form an alcohol. That process, it's not really a mechanism type as such, but we call that hydrolysis. When pretty well anything reacts with water, we call it hydrolysis. Hydro, water, lysis, breaking apart. Either being broken apart by the action of, or breaking apart water itself. Anytime water reacts, it's not going to be water at the end, is it? So the water would have been broken down. We call it a hydrolysis reaction. We're not going to show a mechanism for this, but we are going to write a balanced equation. So in the first step, we had our butene reacting with sulphuric acid to give us this alkyl hydrogen sulphate product. Saturated now, double bonds turn into a single bond. Either one of those two middle carbons has gained an OSO3H, and the other one gained the H from sulphuric acid. Step 2, then, if we're going from alkene to alcohol, would be to show, and as I said, there's no mechanism here, we're just going to write an equation, would be to show that alkyl hydrogen sulphate reacting with water. Now, you pause, or at least just think while I'm talking, what alcohol would sensibly be expected to be formed from this reaction? What do you reckon? And the answer is butan-2-ol. So the logic behind that, when you're looking at it, the way you'd have worked that out is because, well, look, this is where something of interest is in this molecule. Alkanes are really unreactive. So if that was butane, nothing would happen. It's this functional group here which makes it reactive, isn't it? So that's where the action is going to happen. Now let's also think about what the other product must be. Have a think about it. What we're doing, we're kicking off OSO3H, we're adding OH. But it's coming from H2O, so there's a second hydrogen in H2O. Look at the balanced equation, you'll see that basically what's been dropped off here is an S, 3 O's and a H, and there's also an O and 2 more H's. The other product is sulphuric acid. Now, that's interesting. So in the first step, we used concentrated sulphuric acid, and that led us to this alkyl hydrogen sulphate. If we then took our product and added it to water, just diluted it, then it wouldn't just dissolve, it would react with the water. The water wasn't present in that first step because we were using concentrated sulphuric acid. You will use it for yourself eventually. I'll just describe it now. It's colourless, it just looks like sulphuric acid. But when it's concentrated, it's actually quite oily and viscous. It's actually quite a thick substance. There really isn't much H2O in concentrated sulphuric acid. Hence it not dissociating and giving off H+ ions, which hopefully you're already aware is something acids do. So when you add water, which wasn't present in step 1 in any great abundance, then this other reaction happens. And at that point, the sulphuric acid gets reformed. So what could we say about the action of sulphuric acid in this process, in the overall butene to butan-2-ol process? Again, I'm hoping that you're thinking for yourself at the moment. Well, from start to finish across 2 steps, we can say that the sulphuric acid acts as a catalyst, and hopefully you were thinking that. Why is it a catalyst? Well, we talked about free radical substitution before and ozone depletion, and we said the catalyst gets regenerated. So the sulphuric acid's used up here and reformed later on. It's probably not concentrated when it's formed. It depends on how much water you put in. If that was a few drops of H2SO4 and then you add 10 litres of water, then that's going to be very dilute. Fine. But there you go. So over 2 steps, from butene via this alkyl hydrogen sulphate, which gets formed and then used up when we do something else to it. The overall equation there, if I just squeeze it into this space, across 2 steps, is butene plus sulphuric acid. It was used up and then reformed, so that cancels out. Makes this, but then gets used up, so they cancel out. So it's actually plus H2O. Makes butan-2-ol. However, I must stress, if you put butene or any alkene for that matter and water together, nothing happens. You need the acid catalyst here. Now, this is a mechanism that you'll be practicing a little bit of, but there's also another mechanism, as I said earlier, that we haven't studied yet and won't for a little while, where an alkene reacts with H+ to make an alcohol. Basically, it's the same overall equation, but a different set of steps in between. We'll study that separately, and I'll remind you about this one when we look at that. So that's it for today, as simple as that. I just wanted you to see this mechanism. There are some questions for you to practice on, so if you check those out now, it's just more mechanisms. Have a go at drawing, have a go at naming, get them right. It's really important that all those arrows are perfectly placed. The truly final thing now, I just really can't emphasize this enough. You'll get sick of hearing me say it. These arrows have got to be perfect. From the double bond to the H, which is delta plus. From the HO bond to the O. Intermediate, that's the carbocation with the correct structure, with the plus and the H placed correctly. And then here, this arrow we said, from the lone pair on the single bond O- of hydrogen sulphate to the C+. and the hydrogen sulphate with its charge and everything has to be correct. But no, you don't have to show it all expanded. You could have just shown it like this, OSO3H minus, or OSO3H with the minus shown where it more realistically is on the negative. You could have had that arrow coming something like that. Both of those are acceptable. It doesn't have to be expanded, but I want you to see that. I want you to be aware of it. That's it for now then. Check out the questions. There isn't much for you to do. Plenty of practice though, and that's it for now. See you soon.